Hello everyone, so today in this video we are going to discuss this question infected tree which is asked in Codeforces Round 798 Div.2. In this question we are actually given a binary tree and along with that we are given that the root 1, that is the binary tree is rooted at node 1 and that node 1 is given to us to be infected in this question. And at every second, suppose at t is equal to 0 only node 1 is infected, at t is equal to 1 its child got infected, at t is equal to 2 its other child, children's of children's got infected, and so on. That is at each second, or at each after each second the neighbors of the infected node gets infected. And what we are given that suppose we can remove any node. So let's me come to the pane. Suppose this is my node, this is my node, this is my node, and suppose this node is infected. The node which I am marking right now with shading is given infected to me. So let's suppose at this instant I decided to remove this node, the node which I marked with cross. I decided to remove this cross node. So these two nodes which I'm shading with yellow will not get infected. The nodes which I'm actually shading with yellow will not get infected, and these two nodes will remain safe from getting infection. In this question we were told that the node which we had removed, like here I may marked crossed the node which I had removed should not be counted as non-infected node. So the non-infected node are only two, these two nodes of yellow color. This node is not a non-infected node. This node, as we have removed it, so let's say we consider it's actually not infected, but as we have removed it, we said okay, it is useless node. So only useful nodes which are not infected are the yellow ones which I colored it. So in this case our answer is 2. So this is the whole question. Let's deep dive into the question with the help of some examples. Let's consider this example first. In this example, we are given actually there are 7 nodes. The nodes are 1 with the children 2, then 1 with children 5, then 2 with children 3, then 2 with children 4, and 5 with children 6, and 5 with children 7. And initially the first node, that is the 1, is given infected to us. So what we will say is, let's say we removed 5. If we remove 5, we can easily say that let's say at t is equal to 0, our one node is infected. So what we will do at t is equal to 1, or I can say let's say at t is equal to 0 only. I decided to remove the node 5. If I decided to remove the node 5, and here it is also given in the question that we can only remove one node at one instance. So here it is written that in the question, so here as it is given, the following process takes n times. So what we can say is at 1 second we can do only one operation. At 1 second we can do only one operation. So what I'm saying actually is at an instant we can remove only one node. So let's say I decided to remove the node 5. At the time when I'm deciding to remove the node 5, the node 2 also becomes infected. So I decided let's remove the node 4. As I decided to remove the node 4, the node 3 also gets infected. So total number of nodes which are not infected and are useful to us are these two only, 6 and 7. 6 and 7. So my answer in this question is 2. In this way, there are many. In this manner, I can also save 3 and 4. But the maximum number of nodes which I can save is only 2. So in this question, we have to return the maximum number of nodes, or I can say the maximum number of vertices which we can save from the infection. So let's understand the approach of this question. So let's say the tree given to me is this 1, 2, 3. Let's discuss one more example, 4 and 5. So what should I decide? What should my approach is? As I know that the 1 is infected. So my approach should be, let's remove 2. Because if 2 is removed, so our nodes which are safe to us would be 3, 4 and 5. Count is 3. So if the node, any node at any instant, not only the root but any node having any only one child, so it is better to remove that child, so that the children's of that child, here it is 3, 4 and the grandchildren 5, will be saved from the infection. So let's make a big tree and let's discuss the approach. There is a very good example. Let me open that example here. I found a good example which will help you to understand the question more in a more better way. Okay, let's take this example only, the last example. This is a good example. This example will help you to understand how the question actually works. So what we are given is 1 is connected to 2, 2 is connected to 3, 3 is connected to 4, 4 is connected to 5, 4 is connected to 6, 3 is connected to 7, 2 is connected to 8, then 1 is connected to 9, then 9 is connected to 10, and 9 is connected to 11, 10 is connected to 12, 10 is connected to 13, 11 is connected to 14, and 11 is connected to 15. So what should be your optimal approach? You will say, okay, here I can say on the left side 1 is infected. On the left side of 1, what I can see in this section, that 1, 2, 3, that is there are 7 nodes. On the right section I can say there are 7 nodes. So I can say, okay, both are containing the 7 number of nodes. So let's say I decide to save, let's say, let's say decided to save delete 9 and save these much nodes, and I decided to infect 2. So okay, 2 gets infected. After that, let's say I decided, okay, there are 2 nodes 3 and 8, so I decided to remove 3, because of which 8 got infected and the infection stops. So our answer would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The answer would be 10. So let's see the answer. The answer in this case is 10 only. Okay, so answer coming out to be 10 only. So let's change the approach a little bit. We will say, instead of deleting 9 first, let's say we delete 2 first. So if we delete 2 first, so we can easily say that this section and this section remains safe from infection. So 9 got infected. Now let's say I decided to remove 10. So 12 and 13 will remain safe from infection, and 11 got infected. Now let's say I decided to remove 14. So 15 got infected. So our answer would be 1, 2, 3, 4, 5, 6, 7, 8. So the answer would be 8, which is of course less than 10. So this won't be the optimal approach. So here we can see that standing at 1, we decided whether to take the right direction or the left direction. If we decided to remove the node at the right direction, we can see that we will be easily be able to come up with the answer 10. But if I decided to remove the left node initially, that is 2, then I can easily be able to see that I will get the answer as 8, even though on the right side of 1 there are 7 nodes, and on the left side of 1 there are also 7 nodes. So at any instant deciding that the left side contains a larger number of nodes, or right side contains a larger number of nodes. So if we decided to remove the node from the side which contains the larger number of nodes is wrong. So the important observation is, if left side contains more nodes or right side contains more nodes, if left side contains more nodes, this means remove the node, remove the left node, remove left one. Or if right side contains more node, then remove the right node, because of which infection do not gets towards the right node. Is that these are actually the wrong statement. We don't have any proof of it, and we can easily be able to see in the above section that both are containing the same nodes in the right side and the left side of one. But while choosing the left side, while choosing the left side means while cutting the value 2, or so that the infection will not increase on the left side, we can see that our the maximum number of nodes which you can save is less as compared to when we remove the node 9, which is on the right side. So we can easily say that this observation that the if left is more than remove left, that is remove left because of which the infection on left side will not increase, or if right is more, remove right so that the infection on right side will not increase, is actually wrong. So this is wrong. This is our observation 1. So then second observation which you can come to this is, let me remove some of the sections so that we will get free space to discuss further. Okay, let's say this is our tree given to us. So what our approach to this question is, at every node we will make a check, or we will set how many nodes are present right to it, how many nodes are present left to it. So we can see in one, 7 nodes are present right to it and 7 nodes are present left to it. We can see in case of 9, 3 nodes are present right to it and 3 nodes are present left to it. We can see in case of 11, 1 node is present right to it, 1 node is present left to it. In case of 15, we can see 0 node is present right to it, 0 is present left to it. In also 14, we can see 0 is present right to it, 0 is present left of it. In 13, we can see 0 is present right of it, 0 is present left of it. 0 number of nodes are actually present right of it, and 0 number of nodes are present actually left of it. In 12, it's again 0, 0. In 10, it's again 1, 1. In case of 2, it's 5, 1. 5 nodes are present left of it and 1 node is present right of it. In case of 3, it's 3, 1. In case of 4, it's 2, 1. In case of 4, it's 2, 1. In case of 8 is on when I'm saying of left side, you have to see the left child and its child, and when I see the right side, you have to see the right child and its child. In the left side, you can see there are no node. In the right side, you can see there are no node. So left and right 0, 0. Similarly for 5, 0, 0. Similarly for 6, 0, 0. And similarly for 7, 0, 0. So what I made is, for each node I had written the number of nodes which are present to the left of it and the number of nodes which are present to the right of it. Actually, the solution which we are going to discuss in this question is order of n solution, in which we will traverse the whole tree and find out the answer. So the first part is, we had write all the nodes which are left of it and right of it, the number of nodes which are left of it and right of it. The next step would be, we go to each node, we make a DFS call at 1. Let's say we make I'm marking with red, we made a DFS call at 1. We will ask him how many nodes which are present left to you and how many nodes are present right to you. It will say, okay, 7 nodes are present left to me and 7 nodes are present right to me. So I make a call on the left side, left child, that is 2, and I will make a call on the right child, that is 9. The most important thing, how I make a call on the left child and the right child. Okay, so let's say I decided to make a call on the, let me make the screen a little bit larger. Okay, so let's say I decided to make the call on the left side. As we are making DFS, so we know that in the case of DFS, we do the code something like this for auto I colon graphs of child. Then we say if the child is not visited, then we make a call or DFS call to it. So as we can see that when we make the DFS call to it, it is actually a recursive call only. So we are actually talking about how we will making the recursive calls. While doing DFS, we only do one recursive call. One that is not actually one recursive call, but we will do a recursive call on all of its child. We do recursive call on all of its child, but here there are only two child. Here also we are actually doing recursive call on all of its child, and only there are two child, so we are doing recursive call on both of them. But the way in which we are doing the recursive call is a little bit longer. I'm telling you how we will do the recursive call. So when I'm doing the recursive call, the on node 1, when I see the node 1, it has two child. On the left side the value 2, and on the right side having value 9. Okay, so when I'm doing the recursive call on the left side, what I will do is I will mark, okay, the next child is 2, and I will mark graphs, and all the things that I put visited, and so until I will send. Apart from that, I will send one more value, that would be answer. See clearly, answer plus. You will now I will tell you what is answer, but remember, answer plus. I will send 7 minus 1. Okay, let's first understand what does this answer plus 7 minus 1 means. We will discuss later on about what is answer. First, let's understand 7 minus 1 means. When I am doing a recursive call on the left side, this side, when I am doing a recursive call on 2, I am saying, not actually I had done, I am just saying, when I made a recursive call on side left, I am saying I decided to remove 9, and I make a recursive call on left side. Again I am repeating, when I does a recursive call on the left side, what I am thinking in my mind is I am making a call on left side because I removed the right child, that is 9. And if I remove the right child, that is 9, it means I have saved out of 7 6 nodes. The 7 nodes are present on the right of it. I have removed 9, so only the number of saved nodes are 6. That's why I have written 7 minus 1, that is 6. Okay, and why I had add answer to it? Initially the answer is 0, but as it is a recursive call, this answer plus 7 minus 1 will become answer of the next recursive call. So at the end, when we reach the nodes, we have a value answer, and at the end we will take the answer of all the cases. When we make a recursive call on right, we will call on 9. Let me remove something. Okay, here it is 9. When we does a recursive call on 9, we will say, okay, I had made a recursive call on 9, and I say, actually I am thinking that I made a recursive call on right side, that is 9. Why? Because I had removed 2, because of which these 7 nodes which are present on the left of 1, will get saved. So I will say, okay, I will call recursive call on 9, I will put graphs visited and so on, and I will send the answer to be answer plus 7 minus 1. This 7 is for, why this 7? Because I made a recursive call on 9, that is the right side. And I said the left side contains the 7 nodes, and I deleted the node with value 2, because of which all the 6 nodes which are below which are actually the children of the node 2, children and grandchildren of node 2, will get saved. That's why I put 7 minus 1, that is 6, and answer plus 7 minus 1. This will become the answer. This answer plus 7 minus 1 will become actually new recursive call. I'm doing is recursive calls, and this way at the end, when we reach the leaf nodes, we will take the max of all the answers, and we will get our final result. So now this is the approach. I know it might be possible that it looks difficult to you. So let's go into the code section to understand how we can write the code for the same. So you can start understanding the code from, okay, from this section only. Okay, let's first what I had done is, first I had made a vector of pair vk, where vk of I represents the number of elements on the left of I and the number of elements on the right of I. I will fill this vk not right now, but later on when I have made a DFS call here. Actually, I made 3 DFS. You can do it only in one only, but because matlab, I had write this code some days back, that's why I'm actually does 3 DFS call. It's up to your choice. You can make it into 2 also, but the way I feel easy to it, that in that manner I had done that. So let me open the correct code. So this is the correct code. What I had done is the vk of I, the number of elements on the right of I and the number of elements on the left of I. Then this is the input LLAB, scene AB, graphs of A dot pushback B and graphs of B dot pushback A. I made the graph. I marked the graph as name graph1, not graph. Okay. Then I made another 2D vector, that is graphs. And first I make and this visited 3. I write down the name as visited 3. Then I made the DFS call. What I done in this DFS call is I've actually put 2 things. One is graphs1 and other is graphs. So this is my DFS 3. So what I actually done is in this is, let me explain you what I done in this DFS is. Actually, when we are, let me make it full screen. Actually, when we are making a call on DFS, when we are actually making a call on DFS 3. So actually, when we make graphs, what we usually do is, let's say this is my graph 1, 2, 3, and this is 4, and this is 5, let's say. So in the adjacency matrix of 1, we will see 2, 3. In the adjacency matrix of 2, we will see 1, 4, 5. In the adjacency matrix of 3, we will see 1. In the adjacency matrix of 4 and 5, we will see 2. This is our adjacency matrix look like. But I want that the adjacency matrix should be look like this. Now what I am trying making is, I will remove this. Let me cut it out so it will be hard. I will remove this. See, here it is, should be 1. So I will remove this. What I want is my graphs1 is my previous adjacency matrix which you see right now, and after doing some cut, the graphs which is my new adjacency matrix would be. So my new adjacency matrix would be this only. Okay, this would be my new adjacency matrix. What does new adjacency matrix represent? That graph 1 has 2 children, 2, 3. 2 has 2 children, 4, 5. We are not considering the parent of 2. 3 has no child, 4 has no child, 5 has no child. We are making the new adjacency matrix like this. Why we are doing this? Why we are from the adjacency matrix of 2 we are removing 1, saying that we will not consider 1. I will tell all of you these things to you later on in the video. Then in the graphs, then the graph which is the adjacency matrix is actually this, what I'm showing you in the paint right now. Then what we had made is, then we had made another visited, and we have made a DFS call again. Now the previous DFS call is DFS 3. Now this is normal DFS call, and you can see in this I had passed VK here. You can see I had passed VK here. That VK is actually this DFS call, in which you can easily be able to see I had done VK of child is equal to val1 comma val2. That is val1 number of childs are present on the left of child, and the val2 number of childs are present on the right of child. And this way I return the val1 plus val2 plus 1. This is actually the total number of child represented send it from that node. You can easily be able to make the DFS call and find out the how many nodes are present with the left of it to the right of it, and you can easily be able to save. How I saved it? I saved in the form of VK. Suppose I want to know the how many child are present on the left of 1 and the right of 1. So I asked VK of 1 dot first, VK of 1 dot second. So it will tell me the number of childs are present on the left and right. And the third DFS and that I made a variable final answer. As I said you, I will make variable answer and final answer. Out of all the answers, I will find the max of it and will get to know the final answer. I made a DFS call, uh, passing final answer and answer as my parameters. It might be possible that you are thinking that if I calling on both left and right side, don't you think you should not think that it is an exponential time complexity of the power 2 की power n? The reason being in the graph only we can see that we are making a call on the left side and the right side. When we are making a call on the left side, we are thinking that we actually deleted the right node, and when we are making a call on the right side, we are thinking that we are deleted the left node. So we are only making if we see broadly, we are only making a call on left side and the right side, which is actually DFS. We are making the DFS call on the child. Here also we are making the DFS call on the child, that is left child and the right child. Then what we had done is we had called this DFS1 now. First we have made a DFS3 call, the DFS1 call, in which I passed final answer and answer. Then this is the code of it. Then you can see this what I had done. Answer plus k1 you can see, answer plus k2 you can see. That one k1 k2 will be actually here you can see that what the k1 k2 are left minus 1 and right minus 1, max of 0 ll comma left minus 1 and max of 0 ll comma right minus 1. And then I made a DFS call on the you can see I have passed child 1. It means I made a DFS call on the right side, saying that I have considered the left section, that is answer plus k1, and here you can see that the k1 is actually left minus 1. And when I made a DFS call on the child 0, that is on the left side, I said okay, I made on left side, so I consider, it means I considered the right side, that is answer plus k2, where k2 is right minus 1. If the graph child size is 1, as I said you, if the child size is 1, it is better to remove the child, so that the nodes which are below the child will remain safe. And at the end we will what I had done is we will then final answer equal to max of final answer comma answer, and here you can see the parameter answer. In this way we had code out this question.